Ever wonder how a simple, shiny piece of plastic completely revolutionized how we listen to music? Welcome to our explainer on audio compact disc systems. Today, we're breaking down the incredibly precise engineering that made the CD and digital audio itself a reality. It's an amazing story of physics and math, so let's jump right into it.
Okay, here's our roadmap for this module. We'll start with an introduction to optical recording, then move through disc dimensions and the recording process, and look at playback mechanics. After that, we'll tackle signal encoding, error correction, and finally wrap things up with digital to analog conversion.
All right, Section 1, Introduction to Optical Recording. And really, the big fundamental shift we're talking about here is moving away from physical, analog magnetic systems to the absolute microscopic precision of optical digital data.
So why make this leap? Well, the advantages of the compact disc over magnetic tape are just profound. We're talking about the total elimination of analog noise, that underlying tape hiss, plus incredible frequency response and a surface that literally resists dust and wear. But of course, this massive leap in audio fidelity came with a trade-off. We're looking at much higher manufacturing costs and a completely new, exponentially more complex recording process. To really grasp that complexity, we have to think on a microscopic scale. Picture this. Each little data pit on a CD is exactly 1 micrometer deep and half a micrometer wide, with the track separated by just 1.6 micrometers. That is unbelievably tiny. We're looking at the physical topography of digital sound, etched with just astonishing accuracy.
Moving on to Section 2, Disc Dimensions and the Recording Process. Let's see how they actually make these things.
The specifications for a standard CD are mathematically unforgiving. A disc is exactly 1.2 millimeters thick, 12 centimeters across, and holds 540 megabytes of data. To read that, the optical pickup scans at an exact 1.2 meters per second, capturing a 44.1 kilohertz sample rate at 16 bits. When you do the math, that yields a staggering data flow of over 4.3 million bits per second. That's a lot of data flying by.
So how do we physically manufacture that? The workflow is rigorous, to say the least. First, a perfectly polished glass master gets coated with a microscopic layer of photoresist. Then, a modulated laser beam exposes this layer, moving from the center outward. We develop and etch those exposed areas to create the physical pits. Next, that master is silver-coated and nickel-plated to create a rigid stamper. Finally, the actual polycarbonate disc is pressed onto that stamper and sealed with a protective lacquer. It's a real journey from glass to plastic.
Now, during that initial laser exposure step on the turntable, engineers face a really unique physics problem. As the laser moves from the center toward the outer edge, the track radius gets larger, right? So to keep the laser scanning the surface at a totally constant velocity, the driving motor actually has to slowly, continuously reduce its rotational speed. It's a brilliant mechanical dance. Okay, Section 3, Playback Mechanics and Geometry. How do we actually read this newly stamped data? Inside your CD player, a laser directs light through a lens and a half-silvered mirror right onto the disc. Now this mirror lets the initial beam pass through, but it redirects the returning, reflected light straight into a photodiode. The player's control unit uses those exact photodiode signals to constantly adjust the servo system. It actively dials down the motor speed, dropping from 500 RPM all the way down to 200 RPM as that laser moves outward. The real magic of reading the data relies on the physics of light interference. When the laser hits a flat surface, what we call a land, the reflection comes back in phase. That's constructive interference. You get full reflection, and the system reads that as a logic 1. But when the beam strikes a pit, it bounces back 180 degrees out of phase. That creates destructive interference, which essentially cancels out the light, and that registers as out logic 0. So cool, right? And here's a fun fact you might not know. A CD is always played from the inside out. The innermost track starts at exactly a 25 millimeter radius from the center and ends at an outer radius of 58 millimeters. Because the player has to maintain that constant linear velocity we talked about as the radius grows, the physical spinning of the disc literally slows down as your music plays. Let's dive into Section 4, Signal Encoding and Processing. This is where we format that raw data.
You might be wondering, why 44.1 kilohertz? Well, human hearing naturally caps out at about 20 kilohertz. The Nyquist theorem tells us we have to sample the audio at slightly more than double that upper limit to recreate it perfectly. Hence, 44.1 kilohertz is established as the standard. Multiply that by 16-bit audio across 2 stereo channels, and we hit a massive baseline processing requirement of just over 1.4 million bits per second. To manage those millions of raw bits without physical reading errors, engineers use something called 8 to 14 modulation, or EFM. It's exactly what it sounds like, converting 8-bit words into 14-bit words and then adding 3 little merging bits between them. Why? Because the physical laser actually needs a logic state, a pit or a flat, to last for at least 3-bit times but no more than 11-bit times. Standard 8-bit data simply can't guarantee that physical spacing, so EFM completely solves that electrical issue. Think of all this data being framed into tiny, perfectly timed blocks, specifically 136.2 microseconds of audio per frame. To check for errors as it plays, special parity bytes are dropped right into the middle of the frame, literally splitting the raw digitized audio data right in half. And added to the very front of that frame is a control and display byte. Think of this single byte like a GPS coordinate. It handles all the essential locational tracking, ensuring the laser knows exactly where it is in the song at any given microsecond. When you put it all together, you get this final, highly structured 588-bit frame. A 24-bit synchronizing word kicks it off to get the timing right, followed by those EFM converted words we just talked about, all meticulously stitched together by merging gaps. This exact mathematical alignment is what keeps the laser perfectly on track. Moving to Section 5, Error Correction Countermeasures. Because, let's face it, discs get damaged. Since discs inevitably get scratched and smudged, we need some serious countermeasures. The system actually scrambles and delays the data, alternates bits between the left and right audio channels, injects parity bytes at the middle and the end of the frames, and uses cross-interleaving over 112 frames. It sounds incredibly complex, but this deliberate data scattering ensures that a physical scratch doesn't wipe out consecutive pieces of audio. It makes a damaged disc completely playable. Just to picture how clever this is, because the left and right channel data is so aggressively interwoven, a scratch running across the physical track will almost never destroy both stereo signals at the exact same moment. The unblemished channel can actually be used to mathematically calculate, guess, and seamlessly cover up the missing audio. It's like having a built-in safety net. And finally, Section 6, Digital to Analog Conversion. This is the last step in the chain. This right here is where cold binary code becomes the actual music we hear. It uses a binary ladder network, which is essentially a series of resistors forming a physical bridge between rigid digital code and smooth analog voltage. It steps the signal all the way down from the most significant bit to the least significant bit. It accomplishes this through some absolutely brilliant resistive balancing math. Every single node in this circuit perfectly maintains an exact 2R resistance balance to both the source and the ground, routing the electricity flawlessly without distortion. And it leaves us with such a profound thought. How remarkable is it that microscopic, rigid, mathematically unyielding binary code, calculated through perfectly balanced little resistors, can flawlessly reproduce all the fluid, emotional warmth of a human voice? Thanks so much for joining me on this explainer. I hope you learned something new.